औज़ु बिल्लाहि मिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम। Dear student, Assalamu alaikum. This is our fifth lecture on advanced stereochemistry. Today our topic is stereochemical terminologies for sugar, because there are different terminologies of stereochemistry which are used for the sugars. The course is the today lecture is for the students of MS Chemistry with organic specialization. Key concepts of the lectures are isomerism in sugar analogues, DL sugars, alpha beta sugars, anomeric and epimeric carbon, enantiomeric sugars. We will go through all these concepts in this lecture, and we will elaborate in detail the terminologies of sugars in terms of stereochemistry, like DL sugars, alpha beta sugars. These are the terms which are used in the stereochemistry. If we look at the types of isomerism in sugars, then there is possibility sugar may exist in the form of enantiomers, and their isomers can be anomers, and their isomers can be optical isomers, and their isomers can be aldose ketose isomers, and finally their isomers can be epimers. It means a simple sugar can exist in a pair of enantiomers, a pair of anomers, a pair of anomers, a pair of optical isomers, a pair of aldose ketose isomers. These slides show the types of isomerism in sugars. We will discuss all these types in next slides. Stereochemistry of carbohydrates. There are two forms of glyceraldehyde. Glyceraldehydes, the simplest carbohydrate. Two forms of glyceraldehyde. Glyceraldehyde, the simplest carbohydrates, exist in two isomeric forms that are mirror images of each other. You can see that the two enantiomers are mirror image. When the substances are mirror image but non-superimposable, then they are called enantiomers. This is the simplest sugar. This is L-glyceraldehyde and this is D-glyceraldehyde. These two are enantiomers. The relationship between the L-glyceraldehyde and D-glyceraldehyde, that these are enantiomers. Why this is called L-glyceraldehyde and this is called D-glyceraldehyde, I have discussed in my earlier lectures about the nomenclature, but again I will told you that if we look at this carbon, this is the chiral center. Here OH group is on the left side. Here this is the chiral center, chiral carbon. Here OH group is on the right side. That is why we gave the name D-glyceraldehyde. D usually used for right side and L is used for left side. These are the conventions that I have told you earlier, that the capital N, capital D are the conventions. That is why we say that this is the glyceraldehyde, L-glyceraldehyde, and this is the D-glyceraldehyde. When we place the mirror, we can see easily that this proton reflect this one and this aldehyde group reflect this one. But when we place these groups on this group, then these are non-superimposable mirror image. Stereoisomers, these forms are stereoisomers of each other. Glyceraldehyde is a chiral molecules. It cannot be superimposed on its mirror image. The two mirror image forms of glyceraldehydes are enantiomers of each other. Chirality and handness. Chiral molecules have the same relationship to each other that your left and right hands have when reflected in a mirror. You can see that is why chirality means hand-handedness. Our one hand is mirror image of the other hand, because our thumb is going to reflect the other thumb, our forefinger is going to reflect the forefingers, means forefinger of right hand and left hands are going to reflect. But when we placed our hand over each other, then these are non-superimposable, means our thumb is going away. Similarly, our forefinger is going away from the other four fingers. That is why this is called chirality. Handedness, socks, shoes, these are all chiral objects. Chiral objects cannot be superimposed on their mirror image, like hands, gloves, and shoes. A chiral object can be superimposed on the mirror image. Drinking glasses, spheres, and cubes. Any carbon atom which is connected to four different groups will be chiral and will have two non-superimposed mirror image. It is a chiral carbon or a center of chirality. If any of the two groups on the carbon are the same, the carbon atom cannot be chiral. Many organic compounds, including carbohydrates, contain more than one chiral centers. Many organic compounds, including carbohydrates, contain more than one chiral carbon. Important functions of carbohydrates: to provide energy through their oxidation, to supply carbon for the synthesis of cell component, to serve as stored form of chemical energy, to form part of structural elements of some cells and tissues. Biomolecules, a general term referring to organic compounds essential to life. Biochemistry, a study of the compounds and process associated with living organisms. These were some basic concepts about the carbohydrates. Means uh, what is uh, what is the main function of carbohydrates. The main function is to provide energy through the oxidation, to supply the carbon for the synthesis of cell components. And if we focus on the if we see the biomolecule definition, a general term referring to organic compound essential for life, because biomolecules like protein, carbohydrates, enzymes, lipids, these all are biomolecules and they are very important to sustain the life process. And biochemistry is the branch of chemistry which deals the study of compounds and process associated with living organisms. Process, there are a lot of process, like there is a respiratory system, there is a glycolysis, there's Krebs cycle. A lot of these are included in the biochemistry. Carbohydrates are polyhydroxyaldehyde ketones or substances that yield such compounds upon hydrolysis. Example is ribose. This is the simple sugar. If you look at this, the structure of ribose, this is aldoses because it contains aldehyde group. That is why called aldoses. If we look at the structure of the simple sugar ribose, it contains 1, 2, 3 chiral center. Means there is possibility of other isomers, like here there is possibility of optical isomerism, there is possibility of enantiomerism, there is possibility of epimers, there is possibility of anomers. That is why this is the simplest sugar and this is called ribose. Means a lot of isomers are possible from this structure. Classification of carbohydrates. Carbohydrates are classified according to size. Monosaccharide is single polyhydroxyaldehyde or ketone unit. Disaccharide composed of two monosaccharide unit. Polysaccharide, very long chain of linked monosaccharide units. This is the simplest monosaccharide. Monosaccharide, single unit. This is disaccharide. 2 units. This is oligosaccharides, more than 3 to 10 units. Chain containing 3 to 10 units, oligosaccharides. And this is polysaccharide, long chain with possibly hundreds or thousands of units. This is the classification. Means classification of carbohydrates is mainly based upon we use three main classes like monosaccharide, disaccharide, polysaccharides, but there is other which is oligosaccharides. There are about 3 to 10 units comes under the classification of oligosaccharides. Monosaccharide, mono means single, one. That is why it called mono. There is single unit. Di means two. Disaccharide, 2 units. Oligosaccharides, this is also term. It means it contains 3 to 10. That is why it called oligosaccharide. And poly mean many. Poly mean many. They can be hundred, they can be thousands. long chain with possibly hundreds or thousands of units. Again, I have discussed earlier that this is the simplest sugar. This is the L-glyceride and the D-glyceraldehyde. Many carbohydrates exist as enantiomers, stereoisomers that are mirror images of each other. If we place a mirror, we can see that this proton reflects this, and this aldehyde group reflects this one. This is L-glyceraldehyde and this is D-glyceraldehyde. Stereochemistry: a chiral object cannot be superimposed on its mirror image. This is very important point. If any object which is chiral, then it is the property of chiral object that it cannot be superimposed on its mirror image. A chiral carbon is one that has 4 different groups attached to it, like this carbon. This is the central carbon. It is chiral because it contains 4 different groups. If we go towards the priority according to CIP rule, Kahn-Gold-Prelog system, and then we will give OH, because here carbon is directly attached to oxygen. It will get top priority, 1 priority, and here carbon is attached with carbon and next oxygen double bonded, that is it will get the 2nd priority. Here carbon is attached with single oxygen, here is double oxygen, that is it will this alcoholic group will get 3rd priority, and this proton, this is the proton, its atomic number is 1 and it will get 4th priority. These are the 4 different groups attached to the chiral center. Now stereochemistry of carbohydrates continued. The presence of a single chiral carbon gives rise to stereoisomerism. The presence of a single chiral carbon gives rise to stereoisomerism. If a carbon atom is attached to 4 different groups, it is called chiral. If any 2 groups are identical, it is not chiral. Means you can see in this structure that if we look at this carbon number 2, because when we start the numbering, the aldehyde carbon will get one number 1, 2, 3, 4, 5, 6. This is a glucose. This is a 6 carbon sugar. And the number 2 carbon is chiral. Here, if we see 4 different groups, OH1, this is aldehyde 2, and this is 3rd group, and this is 4th group. Again, here in this structure, this is carbon number 3, it is also chiral. It contains a OH group, another group, there is another group, and OH and a proton. That way this is chiral. And similarly the 4th carbon, it is also chiral because it contains OH group and then 2nd group and then 3rd group and then 4th group. Proton is the 4th group. We usually give priority according to CIP rule, Kahn-Gold-Prelog system of configuration, because the element or atom or group attached directly to the chiral center which has greater atomic number will get the highest priority. Similarly, carbon number 5, it is also a chiral center. It's also chiral center because you can see that this is OH1 group, this is 2nd group, this is a 3rd group, this is 4th group. Here it is shown clearly that if more than 1 chiral centers are present, then it's enantiomers, diastereoisomers, then optical isomers, epimers, anomers, aldol-ketose isomers are possible. Stereochemistry compounds can have more than 1 chiral carbon. The maximum number of stereoisomers is 2 power n, where n is the number of chiral carbon atom. Therefore, this compound with 2 chiral carbon atom has 2 power 2 or 4 stereoisomers. The compounds on the previous slides with 4 chiral carbon atom has 2 power 4 16 stereoisomers. here you can see that in this there are two chiral centers, that it contains 4 stereoisomers. The possibility of formation of 4 stereoisomers. For the determination of stereochemistry, we draw Fischer projection formulas. Fischer projection depict the three-dimensional shapes for the chiral molecules with the chiral carbon represented by intersection of two lines. This is L-glyceraldehyde, this is D-glyceraldehyde, and you can see again here OH is on the left side and here OH is on the right side. That is why we say that this is L-glyceraldehyde and this is the D-glyceraldehyde. This is the Fischer projection formula of the glyceraldehyde, which show that these are enantiomers. Now the Fischer projection of carbohydrates have the carbonyl at the top. It is projecting away from the viewer behind the plane in which it is drawn, as is the other vertical bond at the bottom of the image. The hydroxyl group on the chiral carbon furthest from the carbonyl group determine whether the carbohydrate is D, OH on the right, or L, OH on the left. The two horizontal bonds are coming towards the viewer out of the plane in which they are drawn. This is D erythrose, this is L erythrose. Again, here I would like to explain that why this is called D erythrose, why this is called L erythrose. Here the OH groups are on the left side, while here OH group on the right side. That is why when we establish a relationship between the two sugar molecules like D erythrose and L erythrose, I have discussed clearly in my earlier lecture that capital D and capital L are the conventions, means these are not experimental verified values. These terms are conventional, these are not experimental. D erythrose means when OH groups are on the right side, and L erythrose means when OH group are on the left hand side of the chiral carbon. Enantiomer properties, the physical properties of the D and L enantiomers are generally the same. The physical properties of D and L enantiomers are generally the same. D and L enantiomers rotate polarized light in equal but opposite direction. D and L enantiomers rotate the polarized light in equal but opposite direction. This is the simplest diagram of polarimeter. Here this is the ordinary light. Light vibrates in all planes is called ordinary light, and unpolarized light, we can say that this is unpolarized light. The light which has many directions is called unpolarized or ordinary light. When it is passed through the Nicol prism or polarizer, this is polarized lens, then it becomes plane polarized. Plane polarized light means the light which has one direction. This light has one direction, and then this is the tube which contains sample solution. The test sample is placed in the tube, and here is the rotated plane of polarized light, and here is the observer. We see that either the light is rotated in left or right. Then enantiomer properties can be easily determined through polarimeter. The difference between the enantiomers can be only known through polarimeter, means its physical properties, chemical properties, physical properties mean like melting point, boiling point, density, all same. Chemical properties are also same. The difference is only to know the experimentally that when we place the solution in the test tube in polarimeter, then we will get different directions, means D and L enantiomers rotated polarized light in equal but opposite directions. The important point over here is that if the two enantiomers are in equal amount, then they will rotate the plane polarized light in equal but in opposite direction. Understand the point? That means when one enantiomer is 10 molar and other enantiomer is 10 molar, then the rotation will be equal but direction will be opposite. Means one enantiomer rotate the plane polarized light in right and other will rotate the plane polarized in left. The difference can be only created by the rotation, means the rotation can be opposite. That is why through polarimeter we can distinguish between the enantiomers. Then enantiomers that rotate the polarized light to the left is the levorotatory minus enantiomer. The enantiomer that rotates it to the right is the dextrorotatory plus enantiomer. The D and L designations do not represent dextro and levorotatory. These are the convention. I have already discussed that D and L are the conventions. They do not represent dextro and levorotatory. The property of rotating the plane of polarized light is called optical activity, and the molecule with this property are said to be optically active. Measurement of optical activity are useful for differentiating between enantiomers. Measurement of optical activities are useful for differentiating between enantiomers. These are properties of enantiomers. In some instances, only the D or L enantiomers are found in nature. If both D and L are formed, it means if there is presence of both D and L forms in the nature, they are rarely found together in the same biological systems. It is a rule of thumb then means in a biological system there is a possibility of existence of only one form, D form or L form. Usually in nature D form is present because L form cannot be metabolized in the body. For example, carbohydrates and amino acids are chiral. We say that carbohydrates and amino acids are chiral. Humans can only metabolize the D isomers of monosaccharide. Now this is the point you have to understand, that humans can only metabolize the D isomers of monosaccharide. Most animals are only able to utilize the L isomers of amino acids to synthesize proteins. This is the second point, that a lot of animals have the ability to utilize the L isomers of amino acids to synthesize proteins, because proteins are the building blocks of amino acids. Now from this it is shown clearly from the examples that the two forms D and L forms cannot exist in our same biological systems. Means if we see the difference between humans and other animals, then it is very clear that humans can only metabolize the D isomers of monosaccharides, while most animals are only able to utilize the L isomers of amino acid to synthesize proteins. That is why this is the basic difference, and this is very important information for you. You have to keep in mind that there is possibility of existence of only one form, one enantiomers, L enantiomer or D enantiomer in one biological system. It is never possible that one biological system contains both L and D forms. Monosaccharide. Question to ask when classifying a monosaccharide: is the monosaccharide an aldehyde, aldose or ketone? This is a question which can be asked, that a simple sugar monosaccharide is aldehyde or aldose or ketoses. How many carbon atoms are in the monosaccharides? So you can see in this table that monosaccharide classification based on number of carbon, they contains number of carbon atoms: 3 trioses, 4 tetroses, 5 pentoses and 6 hexoses. Means simple sugars can be ketoses, can be aldoses, depends upon, and their classification according to the carbon can be triose, can be tetrose, can be pentose, and can be hexose. This is monosaccharide classification, and you can see the difference between two enantiomer, that here is aldehydic functional group, this is aldotetrose, and this is ketopentose. This is ketopentose because here functional group is carbonyl ketone, here functional group is ketone, here functional group is aldehyde. The difference between the two is that this is aldoses, that's aldotetrose, this is ketopentose, this is ketopentose. Monosaccharide classification, most monosaccharides are aldoses. This is a general point for you to understand that most of the monosaccharides are aldoses. Almost all natural monosaccharides belong to the D series. Almost all natural monosaccharides belong to the D series. The maximum number of possible stereoisomers is 2 power n, where n is the number of chiral carbon atoms. Half of the stereoisomers are D and other half of the L. Means in the sugars, if we apply a formula 2 power n and we got supposed to be there 2 chiral centers and there are 4 stereoisomers possible, then out of 4, 2 will be D form and 2 will be L form. Here in this table there is a number of carbon. There are 3 carbon triose, then there is 1 chiral centers, then stereoisomer possible 2, then number of D stereoisomer 1 and number of L stereoisomer 1. Means if it contains one chiral center, then there is possibility of 2 stereoisomers, one will be D and one will be L. Similarly, if there are 4 carbons and 2 chiral centers, 4 stereoisomers, 2 will be D and 2 will be L stereoisomers. If there are 3 chiral centers in pentoses, then there are 8 stereoisomers, 4 will be D stereoisomer and 4 will be L stereoisomers. Similarly, if there are 6 carbon hexose, then and it contains 4 chiral centers, then there is possibility of 16 stereoisomers. These questions usually asked in the interviews and in the competitive examination, that how many stereoisomers are possible in sugar. If they ask all together, then there are 16. If they ask that how many D stereoisomers possible, then there are 8. How many L stereoisomers possible? There are 8. Then the difference between the two is that total of 16 stereoisomers, out of 16, 8 are D and 8 are L stereoisomers. Monosaccharide classification, this is content, this is aldotetriose, this is aldotetrose. If we place the mirror, this is D-erythrose, this is D-triose, then we can see that the relationship between the two can be established by knowing the stereocenters 1, 2, and it's 1, 2. This is D-erythrose, this is D-triose. It contains 2 stereocenters. This is OH is on the right side here. One OH is left and one is right, and this is called D-triose. Monosaccharide classification, this is D-ribose, D-arabinose, D-xylose, D-lactose, aldopentoses, aldohexoses, D-allose, D-altrose, D-glucose, D-mannose, D-glucose, D-idose, D-galactose, D-talose. These are the different stereoisomers possible, and their names are also different according to their structure. The names are given according to their structures. Physical properties of monosaccharides, most all called sugars because their taste is sweet. All carbohydrates are solid at room temperature because of many OH groups. They form hydrogen bonds with the water molecules and they are extremely water soluble. The relative sweetness of sugars, sucrose is equal to 1, lactose 0.16, this is disaccharide, galactose is 0.22, this is monosaccharide, maltose is 0.32, this is disaccharide, xylose is 0.4 the monosaccharide, glucose is 0.74 monosaccharide, sucrose is 1 is disaccharide, inverted sugar 1.30 mixture of glucose and fructose, 1.73 monosaccharides. The most sweetest sugar is fructose because its relative sweetness is 1.73 and it is monosaccharides. Fructose is the sweetness is greater as compared to other sugars. This was all about the terminologies of sugars, stereochemistry, and now you have to give answer. And this is a simplest quiz or assignment for you. Classify each of the following amino acids as D serine or L serine. This is the Fischer projection. Find RS for each the following Fischer projection. You have to determine the configuration RRS, and again find the RS configuration of each chiral center. Find RS for each chiral carbon in D-galactose. Below feature, this is the structure of D-galactose. You have to give the RS configuration to each chiral center. Thank you very much to listen my lecture, and this is my second time to record my lecture because first time I recorded and I put some handwritten explanation, and this handwritten was rejected by the worthy chairperson because then he asked me to record it again. Then I have recorded the lecture again. You can also use my previous lecture because I have clearly elaborate previous. This is also clearly elaborated. If you have any question, you can ask me, and we can discuss a lot on the terminal sugar. And come in the Google Classroom, and you can ask and put your question. I will give your answer. Thank you. Good luck. Allah Hafiz.